Hello, everyone. I'm Grzegorz, as you may see. I came here to talk about my journey about optimization of triangulation in Napari project. So you may not know it. It's a project for exploring n-dimensional data with annotation. I will show a short example on the beginning. I'm also a CI build wheel maintainer. You might not use it directly, but this is the project focused on shipping wheels for men, and it is used for many popular packages. And I'm also assistant professor on University of Warsaw. Okay, so at the beginning I would like to describe what is the problem, what type of problem we meet, how we solve it. Okay, so first, what is napari? Napari comes from the biologists and bio-related people who have big data, need to annotate, view them, annotate, check if the algorithm is working properly. And instead of everyone in his own computer creating some dummy viewer, we meet at some moment and start collaborating to do this together. So it's theoretically unlimited dimensions. Practically, in most situations, the limit is 10 because this limit comes from the number of dimensions supported by NumPy. It's Python native. It's not something which has Python binding. No, it's just Python with calling some compiled extensions. So it's hackable, and we come from scientific community. Most of the people who are working on it are still active scientists, which has pros and cons. Many things, there's many things available, but many of them are implemented in non-optimal way because it is implemented in enough optimal way for an author who needs it for his research. And our website is napari.org. So, okay, what is the problem? When we would like to annotate data, we may do it in the two ways. We might do labeling, so pixel-wise annotation, so we have exactly the same array as image and label pixel by pixel which class the pixel belongs. Pros, it is really easy to map the data to the annotation. Cons, the annotation is huge. If you have 1 gigabyte of data, the annotation will be also 1 gigabyte with the sometimes maybe even more because it depends on the D type of annotation, you know. These boring things where you need to focus when you are in the compiled language or NumPy or pandas, you select the int 8 and int 64, and it's 8 times difference in the memory consumption, and also performance impacts. So the second option is shapes. In the 3D, it might be meshes, but for 2D, we have shapes. What is the shape? Shape is a sequence of coordinates. There are plenty of algorithms that allow you to check if the pixel is in size shape. It's a little more expensive, but in relatively small size of memory, you can annotate relatively huge data set. But, okay, GPUs natively support rendering textures. So when we have labels, we just send it to the GPU, we provide a mapping, and it's rendered as we would like. For the shapes, we use OpenGL to be multi-platform, and at least OpenGL does not support polygons. It supports triangles. So we need to change every shape that you would like from the sequence of coordinates into sequence of triangles. And what is the problem? We cannot pre-compute it, as many computer games do, because it's user input. And also, it's a tool which allows not only explore data, but update annotation. So it's not that, okay, we make a heavy, expensive calculations on loading the data, prepare everything pre-compute, and user could just smoothly view, because at some moment, user might think, oh, no, here the point is wrongly, and I need to update it. Okay, moving point is most often not a big deal, but the person could think, okay, I need to have additional point because there should be not straight line, but there should be something changed. So we have two things. The first is loading the data. The second is responsibility of interface on the modifications. But in some moments, someone implements shapes, it works well, and then people from special data community comes to us, and they told us that, hey, we like really napari, but it works really, really bad on our data. And their data are starting with around 160,000 of shapes. And you know, the loading time is a little too big. Because, for example, Matplotlib renders this in the 1 minute. We need over almost 4 minutes, and in some scenario even more. And the worst part is that even if someone is loaded data, it lags the interface. So whenever the person tries to interact with the data, the interface is lagging. So, okay, waiting on loading is sometimes acceptable, not always. So, okay, I'm not sure if you see this good. On the upper right corner, you see the zoom of the data. And it is, okay, I don't see mouse. And this, what you see here on the bottom, this gray thing, is the data itself. This is so small that even single polygon is not visible. So I would like to show the scale here. So, okay, what is the data? What is on the simple case? You see the rectangle. On the rectangle, we have, you see that it's not, we have face of the polygon, but we have also edge of polygon. Because of different things in the context of visualization, we need to render separately face and edge to help people understand how the polygon really looks. For example, it better signalizes when we have small gap between two parts of polygon. So, okay, when we think about face triangulation of the rectangle, it's quite simple. You see, it's simple to two polygons. But edge, you see, it's 8 for a single case. We have at this moment 8 polygons, 8 triangles to show. The second case, we could have polygon with holes. And we also could have polygon with self-intersecting edges. I don't have good examples, so I don't show it. But okay, you see the polygon with hole, you see it looks nice. But when you see the face triangulation, you see that with exception to this in the middle, which is not a part of the triangulation, you see that there is 8 triangles to triangulate this. Because if we have a polygon without self-intersection and without holes inside the polygon, the number of triangles to triangulate face is n minus 2, when n is number of vertices. But when we start supporting the polygons with holes, polygons with self-intersection, we cannot pre-allocate memory. We need to perform triangulation and then allocate memory because we don't know what is the size, what is the number of triangles. In the context of speed up, for example, vectorization. And 16 triangles for the edges. The second problem is, okay, how to represent edges. So this is the meter join. This is the most popular. It looks quite nice. But there's a problem when you have sharp angle. When you have sharp angle, you see this second example, it is very, very long. And sometimes user comes to us that they have a spike of length of whole shape. And even sometimes someone show us an example when the algorithm generate a shape, and he need to, every time when he resets zoom to be visible, he stops seeing anything because the spike was so long and taken in the calculation when calculating the zoom that the shapes become too small to be visible. Okay, so we need to use the bevel join. But again, you see, bevel join has one additional triangle. On the meter join, we see the 4 triangles. On the bevel join, we see 5 triangles to represent such a part. So there's a next problem. Maybe another example of what is the difference between meter and bevel. You see this maybe here better than different number of triangles. So it makes another problem with typical speed up of scientific calculations using NumPy vectorization. Because, again, we need to calculate where is the problem, pre-allocation. The typical vectorization in NumPy does not work well. So and the whole goal is to provide such a good visualization that the data scientist could focus on data and understanding if the data are correctly annotated, if we correctly extract knowledge from the data. He should not focus on fighting with the information, with the representation. Also, the best situation is that, okay, user could just make a publication quality feature or presentation quality feature from our tool, because it speeds up every work of every of us. Because we also come from science, and we know that if we have tool which is really nice to make annotation, do everything, but for a lab presentation, for publication, for a meeting with some possible investor from we need to load everything to separate tool, with separate tool chain, with separate file format. You know, I know the better way to waste a week or two than fighting with tool that I'm not familiar, because it doesn't allow me to analyze data, but produce nice pictures. Okay, so I think you might know where is the problem. That's not fully easy to parallelize using the NumPy. But okay, what is the most important? The slowness not always are in the place where we expect. In the context of triangulation of phase polygon, yes, we know where is the problem from the beginning. This is a big problematic chunk of code. Not big, but we know that there is a problem. But for example, for phase triangulation, our performance problems come from the different place, and from the lagging interface. It's totally unexpected for any of place. We are talking on a meeting. Hey, it might be here. Hey, it might be here. Finally, we sit. We try to measure it, and it is in the place where everything was thinking it is clear and fast implementation. And it was quite clear and fast implementation, but no one expected it to be called so often. So, okay. Well, the first things which I would like for you to remember: don't try to guess. You could sometimes, but it's not only this case when we are working on improved performance. And in many situations, if we optimize the code which we guess, not this which we measure, we will have really small performance impact. Because even if you find, for example, some unoptimal quadratic code, it, for example, consumes 5% of the time of execution. And in other place, there is 95% of time of execution. One of the most annoying things is that there are properties that are, this decorator property, but under it was some calculation, which is not cached. And someone else, after half of year of implementation, this property thinks, oh, there's attribute. It looks like an attribute. It does not look like a function. So I don't need to assign it to any variable. I could call it 20 times in the function. And everything starts freezing. Because we are talking about GUI application, so it starts freezing in our case. So, okay, what is the simplest thing? The time module. I think that you know the time module for standard library. I'm not sure it is really great for finding the source of problem, but in many situations, it is enough good to measure overall performance improvement. You just create a script with the reproducible part, but for example, for us, in many situations, we don't want to measure the whole script time of evaluation. For example, in many situations, the problem is also of data loading, which in real life situation comes from the different source, but in the script, we need to load it from some strange file format, and it sometimes takes a long time. But when you have script, it is really nice to use the time module. But there are three things that I think that you might want to use. The first is C profiler with its alternative. C profiler is something which measures the time of execution of every function in your program. And it has two nice things to view this data, because in general, when you run C profiler, you will see obscure table that is not readable. At least for me. Maybe there are some people who know how to read this table, but it's not me. I will show that later. The Snakebees and the Python Professional are, for me, two best tools to investigate this. The next thing is line profiler. So you could profile each line of a given function and check which line is the most problematic. It sometimes is this what you need to find. And the ASV, in our case, this is airspeed velocity. This is tool for benchmarking. It is not useful for debugging and speed up time. It is useful to find a situation when someone else PR after half of year slow down our whole code. Okay, so here is the simplest example of time. So you see we start the timer, put in the next things measure the time, and we could print information about how long it takes. So yes, it allows to only check the big part of the code. If you try to put it in the frequently called function, you will be slowed down by a print. Of course, you could tell me, no, okay, I don't want to do this, but I might make a global variable where I store and count cumulative time and so other things. Yes, you could. But I suggest not re-implementing the profiler. It's already implemented. But it's really, really good in our case for measuring the performance. Especially, we found that some of performance problems depending on the operating system and other things. And we could send such a script to even non-technical user, ask him to execute, and send us the output. And we see if you, for example, change the branch from main to our fixing, if there is a change of performance and not. Of course, there is a time in the command line. On the bottom, you might see the command for the macOS and Linux. For Windows 11, I think it's also present, but I'm not sure. But it counts execution of whole script. So execution of time, of imports, of data loading, etc., which might be not this what we would like to optimize. Okay. C profiler. Built in the standard library, allow to have detailed information about which function takes how many of time and how many times the function is called. Because it might happen that you don't want to speed up the function. It might be not possible to speed up the function. You might just reduce the number of function call by magnitude. And it is the speed that you would like to achieve. And what is really nice in this context, it stores not only information about how long execution of time function takes, but from where the function is called. So there is this information. The problem, it's slow down execution. If you have something which runs for 1 hour, under the profile, it could be few hours. You just need, for example, to cut the data or do something like other. Or try to other profiler. There are Yapi, VMProv, there are some or more. Especially for a big problem, you might want to look on the statistical profilers, which does not do measure of execution of every function. It just makes us constantly ask the process in which state it is, and by statistics measure where the process spent the most of the time. And what is really things that I suggest to use, because of course you could just execute as on the bottom Python -m C profiler the script, and you get profiling of the whole script. You might in the PyCharm or on the other IDE click the button run with the profiler. But in my experience, in many situations, it will be polluted with many obsolete things, with the data loading, with the import time. And for many situations, it will make it unreadable and mess. For me, for most situations, I would like to use the context profiler, where I only profile this part, this exactly part of the code that I would like to profile. And okay, what is important? There is a Python. Okay, this will. So okay, but we have measure performance, and we would like to use it. So the first tool that I think many of you might want to use is Snakevis. It's quite popular. You see the interface. It is the spawn in the web browser. What is the advantage of this? It's good enough to go through the whole stack of execution and see where the time is spent. It has integration for almost everything. You might spawn Snakevis in your Jupyter notebook. You might just run profiler in the notebook and then spawn Snakevis to see what happens. There is a plugin to VS Code. There is many other plugins. It's open source and many people are using it. And it allows to go interactively way through the code, see where is the most time spent and other things. For someone who is using the PyCharm with the professional license, they have one nice feature. They provide a graph of the call. So you don't only you have the graph which is showing directly which function is called from where. And in the situation where you have one function which is called too many times, it is much easier, for example, in PyCharm to find from where it's called. In the Snakevis, the interface is not optimal for this. What not many things people know maybe, at least in my experience, you don't need to run the don't need to profile in the PyCharm. You might just go to tools and load cprofile snapshot. So this which you saved with only the part of code which is interesting for you. The problematic part is that you need to remember that the extension of the file need to be pstat. Because in some tutorials and with current LLMs, it often suggests the extension .prof, and then PyCharm shows the dialog error with loading profile. That's not, and remember that pstat is the extension that you need. Okay, line profiler. This is a dummy example, but I would like to show. So if you have a function, you see the function. You see that the function is not called too much, but it consumes too many time, and you don't see why, where. You might use the line profiler from the PyPI, decorate this function with the profile decorator, run, and it will have information how many times and how long each line takes. This is from integration with PyCharm, but you could do this also from CLI. It works really nice. It significantly slows down the given function, which is profile, but it slows down only this function, which is decorated. Without PyCharm integration, if you decorate too many functions, from me, the output will be unreadable. The simplest example where I found this to be useful, someone use the list as a set. So there is a structure to store visited objects, and it was list, not a set. And it's a problem because for small data it works relatively fast, but for bigger data, you know, the checking if something's in the set is at a constant time, and checking if something's in the list, especially if it's not present, it's linear time. And we ran this line profiler and found, oh, operation if object in storage takes 99% of time. Okay, let's see what happens. And dig. Oh, no one checks even this part of the code, but here is the dummy list not set. You know, this is the power and weakness of Python, that sometimes the data structure allows you to do something which should not allow you to do. Okay, so the last things, the benchmarking. In many situations, I don't see it useful for debugging in general, because it is really generic, but it allows you to just, declare, you may declare the class with proper objects like time create layer. If it has prefix time, it measures time. If it has prefix mem, it measures the memory used. And you might run it on the CI or on your machine and compare two different commits with the performance for a given benchmark. So it's really helpful to show, hey, my solution is really speed up, and it's really helpful to find, hey, this commit is breaking the performance. And also with ASV profiler, we need to run with really specific set of commands, but you might spawn snake vis with this graph, and it sometimes allows us to understand why there is a slowdown, because we see this graph. And you might see here on the bottom some results of of the performance improvement that for some quite big number of benchmarks, I have speed up around 25 times plus. 25 times depending, 2 times to 25 times depending on the used tools. Okay, so I show you the tools that we are used. I think that some of you might have other tools to use. This is which one we found and useful. But the first most important things. In the description, I wrote about Numba, Cython, C++, Rust, but the first thing that you should consider is algorithms. So the most important thing, changing the technology could speed up your code by a factor, by constant factor. For example, it's known that Rust or C is around 100 times faster than pure Python in many operations. So okay, in your case, 100 times speed up is enough, you will be happy. But remember that in most situations, if you have nonlinear algorithm, if your data increase, and in our world it is normal that data increase, changing the technology without changing the algorithm might not solve your problem, and better algorithm in Python might be faster than any other technology. Okay, so what we found? So first, optimize algorithm. Find a place where the algorithm is not optimal. Sometimes it's better to theoretically slow down your code. So add on the beginning of the function which recognize special cases which could be solved faster. And if you have enough these special cases, even the slowdown which comes from additional code which need to be executed will reduce your whole code execution. Sometimes you might push the complexity into the memory. You have some redundant information which comes from other data. The storage of them, for example, occupy an additional next 10% of memory, but calculation of they are so useful that you don't want to calculate them each time. Parallelize, vectorize. So sometimes you might parallelize even in Python, and now with the free-threaded Python, it's not even in Python, but just if you may have option, you might just parallelize. And I see many situations when vectorization is responsive. Instead of for loop, you have pandas data frame, numpy array, dask array, something other, and execute as a vector optimization when other people think about your performance. Okay, so our first case, which is the biggest slowdown, we expect this is a problem. We have polygons, but polygons, we don't have guarantee that edge will be without surface intersecting. The algorithm initial was with quadratic complexity, but it's vectorized using NumPy. There is a faster algorithm, which is n log n. It's sweeping line, but it could not be vectorized using NumPy. So in many situations, this quadratic solution was faster because we have smaller polygons. And this sweeping line requires binary search tree to have the left and right neighbor, and it's not as easy available in Python with performant way which we need. Okay, so what I told earlier that it's vectorized using NumPy, so it gave us this 100 times speed up. And most of our polygons are small, below 20 points. So this is why I told point that many optimization might depend on your data. Sometimes you don't want to use the fast, because you know there's this theoretical big O notation about complexity, but this theoretical big O notation does not take care about constant of the algorithm. And it happens that for small data, for specific data, or for your data, the algorithm with theoretical complexity is better. The good example is quicksort. You know, the quicksort, which is one of the most popular sorting algorithms, has theoretical complexity quadratic. But mean complexity is better than other algorithms. So okay, so we found that we need a complete solution, but maybe first special edge cases. So, okay, there is a proof that you cannot triangulate normal polygon below n log n. No one showed the algorithm which is faster than n log n for triangulation. But if you find that your polygon is convex, so the convex is that if you have any 2 points of the feature, of the border of feature, and have a line between them, there will be no intersection of the edges of the feature. So you might see that the bottom one is convex, the upper one is not convex. So okay, so if we could find that the polygon is convex, we could triangulate it fan triangulation as shown, and it is linear. Because we select one point and draw the lines and we are happy. And it's possible to check it in the linear time. So yes, this is the additional check which we introduced, and in general, it speeds up our triangulation really significantly. You might think about algorithms to check if the polygon is convex, and on the end, we might talk and show if you find the proper solution or hit the same rabbit hole that we think that we have correct solution, but it finally does not work enough good. Okay, so caching. We need to find which polygon is under the mouse to show the information to the user, because he needs to have information about what the polygon represents, what are the additional data connected to it, and so on. There is a really nice algorithm which is really fast, parallelized, and vectorized in NumPy, which checks we have array of triangles, and we could check which triangles contain the mouse coordinate. It's really fast. But we have at least 3n minus 2 triangles for each polygon. So you see, for polygon of size 10, we have, with nice polygon convex with size 10, we have 30 triangles. So even with such algorithm, it was slower. It was slower because we have too many things to check. Our solution, okay, calculate bounding box. We could easily check with the code, we will see if the point is in the bounding box, and then run the algorithm from the previous slide only for the subset of polygons that contains that bounding box contains mouse. Typically, it's 1 or 2 polygons, so it's much faster. So yes, we need to additional memory, store additional memory, do additional calculation. In theoretical situation, when every polygon are on the same stack, additional error code is problematic. But for real data, it's speed up. It's this simple change allow us to stop lagging interface with the mouse interaction. And okay, so vectorize, but not too much. I told you that NumPy, operational NumPy arrays are really, really fast. But you might see these two functions. These two functions do exactly the same. But first is calling the roll, and the second is getting a slice and do edge cases manually. Even for small polygon, second is 2 times faster. For bigger polygons, the second is much, much faster. Why? Because the NumPy roll contains allocation of new array of memory. It is not view with rolled data, but it creates a new array, so you need to additional steps of copying all data. So no, I know that this best second is look worse, it's longer, it's less readable, it's faster. So don't try to vectorize too fast, too much. Okay, so compiled approach. We show that sometimes algorithm speed up helps. It allows us to get better performance. But for example, in our case, we have we do information, and in some situation, we would like to fit with whole set of operation under the 30 milliseconds. Okay, so first what we use Numba. Numba, I don't know who of you know Numba. Numba is JIT compiler for scientific calculations. If you work on the NumPy arrays, if you work on such of structures, you in many situations might speed up your code by just importing Numba and adding the decorator njit. There's a JIT and njit is new JIT, and it's speed up. What is really nice also, there is this cache option. If you use your algorithm frequently, you might cache it to the disk. So even on the next start, it only loads the compilation from drive, not load it from the, not compile it again. So you might see you have pure Python code that might be readable by your Python experts, and it is faster. And if there's inline, so if you have a Numba function, which calls Numba function, it might inline the function that is called. It also is next step of the speed up. The Numba has many limitations. If you override the function after the function caller is jitted, it will not update and so on. So you know, you come to the compiled world. What is important? In some situations, you switch to the for. Instead of vectorization, switch to the for. It works quite nice. So maybe if you like really vectorization, it might be you might not be convinced with this, but it works. There's low problem with maintenance or low problem with this. But what is the problem? Initial compilation takes time. For our interface, we need to do some strategy. Okay, which functions, which type of parameters we would like to, on which action, pre-compile to not have lags in the user interface. Especially, so when someone is creating shapes layer, we call the jitted function with some set of abstract arrays to speed up it. Because otherwise the user will see lag when he starts painting the shapes. Even loadings from drive takes time. So it is visible in the user interface the time which Numba needs to load from drive on the request. Numba is per array type, array dimensionality, and array memory order. So in some situations, we need to run it with the C order and F order. Which is C order, F is Fortran. Okay, sometimes as I show, to get full speed up, you need to rewrite some vectorized operation to the for loops. And for the profiling, if you allocate memory in jitted function with Numba, it is invisible in the benchmark tool that we use. The problematic function is pimpler as size of. Okay, so what happens for our project? We need to rewrite some of functions to fit in the, because also this how you write a function impact the time of compilation. We, in some moment, have over 1 minute of compilation, what is not acceptable. It allows us to fix the bevel join. On the left, you see the version which is before Numba. On the right, you see the version of the triangulation which is after the Numba. You might see these small triangles on the left and the expected size of triangles on the right. Still, even with better correctness of data rendering, we have 5 times speed up. And I think that we might have it even more, but we don't have this. we cannot speed up phase triangulation. It slowed down NumPy version adoption because Numba heavily depends on NumPy, and we have 1 month delay of adopting new version of NumPy. Okay, I have not so many time. Cython. Cython is, you might see it earlier, Python with C-type declaration. So, okay, it's nice. It is compiled. It compiled to C or C++. But it's still readable for a person who knows Python. He might not be able to easily update, maintain it, but he's able to understand it. Also, it allows us to easily connect to the C++ code. We might rewrite to, as you see, to the vector. This is the C++ vector, C++ under the set, and we could rewrite it, allocate, and run it. And if you would like to try to use the Cython, use Cythonize -a. It allows you to find which part of your Cython code is compiled to pure C++ code, which does not interact with the interpreter, which is not. You might see the examples of small change that speed up code 20 times. So our outcome, we speed up 100 times faster, edge plus phase, faster edge triangulation 30 times. But if we meet the problems with float precision calculation, you know this problem 0.1 plus 0.2 is not equal to 0.3. We find much more edge cases. It is a big problem. The sec fault, and it's hard to find what is the cause if the user is not expected how to core dump or provide us a data. And we find a bug in the C-lang compiler on macOS. You see these two functions. There should be equivalent. The first one is working as expected on Mac, and the second one is not working as expected. So in some situation, the first val1 and val2 are equal, but the second calculation is not equal to 0. So our outcome, when we try to Cythonize, it is harder to get a review. Less people know Cython, C++ than Python. We use the scikit build core as a backend. If someone would like to see it, it's in the parsec corp compiled backend. It's part of my PhD project. And we don't test PyBint 11, so it might be even faster. Okay, Rust. We find that the Rust is quite popular for new projects, and we find that it's memory safe. It is fast, and I agree it's fast, but it has lack of stable ABI. It's a problem if you would like to compile two things and they communicate. They need to do this using C API, so you have whole C fragility. So as I told, less known in the community, even harder review of code done in the context of C++ Cython, but has great toolchain built in that allow us to skip some stupid errors, has nicer compiler error to understand what is the problem. RS test is quite similar to PyTest and allow us to do it better. We get 200 times faster, but it does not mean that the C++ solution is slower. We don't polish it enough. Because what is the main outcome? In many situations when the C++ rise segmentation fault, we got exception from Rust, and we might handle it. We might dump the data and have nicer debugging. So this is why we polish. And one of the solutions of problem review, I include the CodeRabbit AI to the project, and it works. It finds some stupid tasks which allow problems and allow to improve code before human in the loop make a review. And we find, using this, we find more edge problems with floats numbers. So summary, use profiler and benchmarks. First change the algorithm, then change the technology. Speed up only required parts. We only rewrite small part of the project. Our project is over 100,000 lines of Python still. If you would like to start compile, don't put the compile extension in your big project. Use the separate package, because you more often would like to modify Python project than the other one. Okay, so Cython is more spectacular, but for our experience has better tooling to understand, better integration with GDB. Okay, and I would like to say thanks to napari community, to SCverse, which provide funds to allow make it possible, and Chan and Zuckerberg initiative, which provides grants for both Napari and SCverse community.
Session, Gregory. We not have questions for this session because time is up and we need to prepare for other speakers. But in case you have questions, please feel free to approach the speaker, or even you can post on Discord the questions. Thanks.